Okay, thank you very much, Andy, for the introduction. As Andy mentioned, the title of this presentation is Fracture and Adhesive Joints, and my co-presenter this morning is Anastasios Vassilopoulos. I just wanted to say that we have in ESIS TC4, we have a very active group looking at fracture in structural adhesive joints. Also, another activity in the adhesion area is peel testing, which Neil Murphy, the previous speaker, has been heavily involved with. And I'll also flag up that there's another presentation later on this afternoon presented by Stefan Marzi, who will be looking at the application of J-integral to adhesive joints where LEFM techniques may not be applicable. So just see how I can. Okay, so just to give you an idea of the structure of the presentation, I'm going to present the first part, where I'm going to give a brief introduction to adhesive joints, and then I'll be talking about some of the test methods that we use to characterize the fracture resistance of joints. Fortunately, we've had quite a nice introduction from Neil on the methods that have been used to characterize delamination resistance. Indeed, there are many similarities between the characterization of composite materials and the techniques we use for adhesively bonded joints, and I'll say why they're applicable. And I'll end up with talking about some of the other test conditions that we're also interested in, and some of which we're currently studying within ESIS TC4. The second part, Tasos will talk more about structural applications, and describe it as testing of realistic joints. He'll describe more carefully what he means by that when we get to that point. So in terms of structural adhesives and adhesive bonding, clearly adhesives offer designers and manufacturers a very efficient way to join materials. They are primarily a joining solution. And one of the great advantages of adhesives is that they give us the capability to bond different materials. They can bond carbon fiber composite to aluminium alloy. They can bond aluminium to titanium, and so on and so forth. So they have a very wide potential, and they're therefore widely used to provide multi-material joining solutions. So if we look at the two applications that we have on this slide, on the left-hand side we have the Airbus A380. So clearly a very complex structure, but the schematic here shows how adhesives are widely used across the airframe, moving from, for example, structural film adhesives in many of the wing structures, including the spoilers and joining of the aliens, through to, for example, more structural adhesive used in the cowling for the engines, for example, and many applications. For example, film adhesives used in the vertical tailplane, in the horizontal tailplanes, and of course, adhesives are generally used in the fuselage, for example, in the glare metal fiber laminate system, which is used in the upper section of the fuselage. So we see lots of applications where adhesives are being used in the aerospace industry. Looking at the schematic on the right, we can see that adhesives are also very heavily used in the automotive industry. And in the case there, you can see a paste adhesive being applied robotically to a car body panel. You can see the blue fillet forming. And again, the adhesive is used quite extensively, and it can join similar materials and dissimilar materials. But what's really critical for using adhesives in applications such as the two we see here is the ability to be able to predict their performance. And that's their performance under a wide range of different loading conditions and service environments. So this is really what we're talking about, methods to be able to do this in this presentation. So if I can move to the next slide, there are many important things we have to take into account when we're looking at the use of adhesives to bond materials. First of all, the adhesive needs to be chosen with careful consideration of the materials to be joined. So we describe these as the substrates. Of course, these substrates will be different depending upon the application and depending upon the need to have lightweight materials and so forth. We'll also we'll have to decide whether we're going to use a film or a paste adhesive. So, for example, in the previous slide, we saw applications where film adhesives were used. Film adhesives tend to be used for large area bonding applications because they're easy to apply. Paste adhesives are more suitable for narrow beads and bonding narrow areas, but also do lend themselves to robotic application. Also, the question of whether we're going to be using a high TG or a low TG adhesive will be important. And something else that's really important with all adhesive bonding is how will the surfaces be pre-treated prior to bonding. This is a key thing, because if the surfaces are not adequately prepared prior to the application of adhesive, then the bond won't fulfill its intended task. And we can see this by an interfacial failure mechanism, which may occur if the surface preparation is inadequate. In terms of bond line thickness, the applications that I've mentioned tend to have bond line thicknesses which can be quite carefully controlled. So the bond line thickness is an important parameter. So quite literally, how thick is the adhesive layer between the two substrates, and how that will influence the failure. In the second part of the presentation, Tassos will talk more about where it's harder to control this, and you may have wide variations in that bond line thickness. But staying on this part, we also have to ask ourselves how long will the joint be expected to last in service, and what are the applied loads. So how can we predict the performance of the adhesive joint? So historically, there have been many test methods that have been developed to measure joint performance. We see three columns of experimental test coupons that can be used. The first two are what I've just described as lap shear and sort of variants upon that. Basically, you can have two coupons, which are the materials that you wish to join, and you can bond those with an area of adhesive. And you can pull that apart to failure, and you can measure the applied loads, and then you can deduce the stress that was required to cause the joint to fail. And you can see the first one would be an example of the single lap joint, very commonly used. And you have variants. You have a double lap joint. You have tapered versions of this, and you have step joints, and you have strap joints. There are many ways of doing that. The problem that we tend to have with this type of method to characterize what's going on is that they do tend to be relatively highly geometry dependent. And what we're after in if you like, in structural design and developing systems which will last for substantial amounts of time in service, is we need to be able to characterize actually how a joint would fail. So we need to have something which is geometry independent. So on the right hand column, we see two examples of fracture mechanics coupons. The first is very similar to the double cantilever beam that Neil has described previously, but in this case we have two substrates which are bonded by a thin layer of adhesive. So shown in red in this is where the adhesive layer will be, and this shown in black would be an initial delamination or an initial defect or insert film. And for example, we could get the same conditions in a tapered beam here. This is a version of the double cantilever beam test, which is called the tapered double cantilever beam because it's height tapered. And this gives us another opportunity to measure the mode 1 fracture resistance. So using fracture mechanics provides us with a framework to describe it in a more simple terms, because although these specimens look simple, the actual stress distributions across the adhesive layer can be quite complicated. So the idea of the fracture mechanics is to provide geometry independent and well-defined conditions at the crack tip from which we can go on and measure how a material structure will behave. So basically, we're talking about the fracture mechanics framework. So if we take a car structure that we see here, the car chassis, you can take any particular part of this component and you can therefore analyze the stresses in that, work out if you have, for example, an adhesive joint at any part in the structure, you should be able to work out from an analysis of the stresses and the deformations, you should be able to analyze the loading mode. Neil introduced us to the three modes of fracture mechanics, mode 1, mode 2, and mode 3. And of course, what's important is when you have mixtures of these modes, we'll find that most of these applications will indeed not be pure mode, but will be some combination of, for example, mode 1 and 2 loading. So mode 1 and 2 loading is the most widely studied of the different mixed mode combinations. In terms of getting mode 1 data for the adhesive joint system, of course, you select your substrate materials, you make sure that your surfaces are adequately pre-treated, and you can form a double cantilever beam. So this would be bonded with the adhesive of interest, and you form a double cantilever beam as shown in the diagram on the left. We pull with a constant opening rate, and you can see a crack which was initially introduced by placing typically a piece of PTFE film in the middle of the bond line during manufacture. That initial defect is then propagated through the adhesive layer. And what we typically want to measure is a cohesive fracture where the failure location remains within the adhesive. If, of course, it runs along the interface, it's telling us that the surface preparation wasn't adequate for the application. Of course, if you have composite substrates, you have another potential mode of propagation where literally the crack can relocate itself and run into the composite substrate, and you end up with an interlaminar failure. And in this case, you're effectively saying that the adhesive layer is stronger, more fracture resistant, I should probably say, than the material you're joining, and therefore is not the weakest link in our adhesive joint system. As Neil was describing, we measure the propagation of the crack, and we then record the experimental data. So this could be, this is a typical load displacement diagram obtained from a mode 1 test, where in this case we had titanium substrates, and we had a structural adhesive typically formed by into a bond line of around about 0.4 millimeters. And to be able to apply linear elastic fracture mechanics to this sort of experiment, we have to convince ourselves that the initial loading is linear elastic prior to crack propagation. So you can see from this force displacement trace, which is obtained from the mode 1 test, that we do have a highly linear initial loading. And one can test this by unloading at different points along the propagation to see that you retain the linearity. And what we find is that for many adhesives, LEFM works well. Where we run into difficulties is where it's not so much that we have a tough adhesive, potentially, but it's that we have a ductile adhesive. And when we have particularly combination of tough and ductile adhesives, then we often find that linear elastic fracture mechanics doesn't provide the route to analyzing the data, and we would look at nonlinear and J-integral methods, which will be discussed later on this afternoon. But you can see here, this is a tough structural epoxy adhesive. We're identifying positions of crack initiation, either nonlinear, where this initial curve starts to bend over, visual, potentially where you see the crack start to run through a microscope, and a 5% offset in initial compliance. Different ways that you can say when the crack starts, and then all of this data will be from the crack running cohesively through the adhesive layer. How do you then go on to analyze this sort of data? Well, the way that you can do it are similar to the ways that have been outlined previously. You can use an experimental compliance approach. For example, you can invoke the Irwin-Keyes equation, very well-known fraction mechanics equation, which relates the rate of the rate of changing compliance with crack length to the energy release rate. Or you can use beam theory. And in this case, what we're assuming is that the stiffness of the adhesive is negligible compared to the stiffness of the substrates. And we're also assuming that the adhesive layer is relatively thin. So if we have both of those conditions, and they are often valid, then we can say that the adhesive layer can be effectively ignored in the compliance relationship without introducing any significant error. So we were looking at these methods a little bit earlier on, but this is how we can see we can analyze the mode 1 DCB experiment. We have two cantilevers, hence the double cantilever beam, and each cantilever is loaded with a force given by P in this schematic, and the load line opening displacement is given by the displacement delta. So that's a total beam opening. And if we have a thickness of H for the upper substrate, which would equal the thickness of the lower substrate here, we can define a crack length, which is obviously the curved length from the load line to the crack tip. Now, in the analysis for the double cantilever beam, we assume for the application of simple beam theory that the crack is built in at the crack tip. So we have a built-in condition, and the way that you apply the beam theory is basically to take one of those cantilevers, assume it's built in at the crack tip, so apply the standard built-in cantilever beam boundary conditions for the crack tip, and you can introduce the compliance term, and we derive the first equation here, which relates the crack length and the axial modulus of the beam and the other geometry to the compliance. And then by applying Irwin-Keyes, we get the first of the beam theory fraction mechanics equations. You can remove the axial modulus from this equation by making it the subject of this formula and introducing it, and you end up with a second alternative form of the expression, which is independent of the axial modulus. Useful if you don't know that a priori. Now, there's a problem with applying simple beam theory, and Gordon Williams did some detailed analysis on this experiment in the early 1990s, and identified that the approach that we've just looked at, where the crack length was the beam was modeled as being built in at the crack length, the crack tip, was actually inaccurate. And what was required was a crack length correction term. So it was necessary to move the built-in condition at the crack tip to move it a distance ahead of the crack, where we could determine an apparent base, because due to beam root rotation effects at the crack tip, the boundary conditions were not actually satisfied. So if you move a step ahead of the crack tip, given by this expression chi, which is an elastic constant, multiplied by h, the thickness of the beam, you move to a the position where the boundary conditions are met. So in the crack length correction term, this chi h term, it accounts effectively for the inaccuracy of the beam root rotation assumption, and also it simultaneously corrects for transverse shear effects within the substrates. So it corrects two terms, root rotation and transverse shear. There's a relatively simple experimental method by which this term can be defined, and of course you can then correct the crack length. You can correct additionally this correction where you have A not being horizontal. The more the beam deflects, then the more the bending moment will be in error by assuming that the bending moment is equal to the force multiplied by the crack length. So this is what the correction factor F does. So Gordon-Williams derived these displacement correction factors to deal with the shortening of the moment arm, and N comes in from the fact that typically to load these specimens we'll attach a load block. This is a typical R curve that we might measure from a mode 1 experiment, and of course you can see how the simple beam theory, the corrected version of the beam theory, and the experimental compliance methods may vary. Typically what we would see in structural adhesives is a relatively flat R curve. Assuming that the crack is running through the center of an adhesive, we shouldn't be seeing fiber bridging effects because they won't be present. We should see a relatively constant value of fracture energy as the crack runs through the adhesive. Moving briefly to mode 2, Neil also described these experiments, and for structural adhesives, of course, we'll have the added complication that we'll have a bond line. But apart from that, the experimental methods are analogous to those which have been described previously. And the method of analysis is also analogous. One can apply compliance methods, or one can apply beam theory and then corrected versions of beam theory to actually analyze these data. And also, as Neil mentioned, for the composite laminates, we have a problem with measuring mode 2 crack lengths. And this is even more of a problem, I would say, in joints than it is in composites. And what we really have is if we're applying a constant mode 2 loading to this particular specimen, this is now a carbon fiber composite set of substrates bonded by a tough structural adhesive. What we can see is inclined microcracks extending very significantly ahead of what we would describe as the main crack tip. So the main crack tip might be defined as the point where you have a continuous discontinuity between the upper and the lower substrates moving from the load line. And when we get into this region, you can see that there's a more complicated damage zone has been developed, which we have to account for. So again, this was described in an earlier presentation by Neil, but we can effectively calibrate the fixture by determining the clamp calibration. This removes much of the problem that we had previously with the particular version of the experiment. This N-loaded split tended to give results which were highly clamp dependent. So all of the different test labs have their own fixtures for doing these experiments, and that was also the case with ESIS TC4. We all had different fixtures, they all had different stiffnesses, and this introduced a large degree of scatter and affected the reproducibility of the mode 2 data that we were measuring. But we were able to resolve that by having this process to calibrate the clamp, and also invoking this concept of using the effective crack length approach. So effectively, we were not measuring the crack length anymore, but we were determining the crack length based upon the beam theory that we were applying. So these are the methods that will effectively describe how we can determine a crack length, and hence the mode 2 energy release rate, G2C, for a structural epoxy. So to conclude with the mode 2 analysis, what we would expect to see if we're looking at energy release rate against crack length is, again, we would expect to see some sort of steady state region developed, whereby the fracture resistance attains a steady state. And for this particular system, we noticed that this was an adhesive where if we tested in mode 1, we had a 1 kilojoule per square meter of fracture resistance. And now testing in pure mode 2, we noticed that the value is around about 5.5 kilojoule per square meter. So a factor of about 5.5 times tougher in mode 2 than in mode 1. And of course, this will be highly material dependent. So some adhesives will show very large elevations in mode 2 to mode 1, and other adhesives will not. So it is material specific. Very quickly with mixed mode combinations where we want to combine mode 1 and mode 2 in the same experiment. Again, we saw some examples in the previous presentation. I'll just show one. This particular method is described as the asymmetric fixed ratio mixed mode test, where you can see clearly the substrates have different thicknesses. This introduces many more complications than we realized initially. Of course, if you have the thickness H1 equal to the lower thickness H2, that becomes the fixed ratio mixed mode experiment, which we are standardizing in ESIS TC4. But with this asymmetric experiment, you can obtain more mixed mode ratios. Again, you can analyze the beam, assume it's built in at the crack tip, apply beam theory and correct it very much in the way that we've described above. And what you want to do in such situations is to develop the mixed mode failure locus. So the experiment that I've just shown you may give you some points sort of in this region. This would be a mode 1 fracture resistance, and this will be the pure mode 2 fracture resistance. And what we obtain to do in a result of these experiments is to determine, in this case, the mode 1 to mode 2 mixed mode failure locus. So we can see how the fracture resistance develops as we move from pure mode 1 to pure mode 2. The problem, well, a complication of developing a diagram like this is that your measured experimental data, which could come from very many different mixed mode experiments, depends upon how you partition the data. And there are different ways of doing this, which have quite profound effects on the failure locus that you measure. Just to summarize very briefly, if you apply the method named after Gordon Williams, you apply a global approach to partitioning the mode 1 and mode 2 fracture energy. And that means that you don't have to focus on crack tip effects. You look at bending moments applied globally to the specimen. If you take a different approach, for example, and you take a Davidson crack tip element singular field approach, this approach basically means that you are looking at the details of the crack tip. You're looking at the degree of singularity at the crack tip, and you are using that approach to partition the fracture energy. And what we found from doing that is that we have a singular field approach looks to be non-physical for the material that we're using. And what we went on to find and conclude is that for materials where we have a relatively significant amount of damage at the crack tip, then singular field approaches were not suitable and gave us a non-physical results to the partitioning scheme. Williams was better, but wasn't perfect. There was recently a new approach developed, which was the SACA, or semi-analytical cohesive analysis approach. This was proposed by Alois Ivankovic and some co-workers, where you basically you work out the degree of singularity that is appropriate for your test conditions and your experiment. So you basically will determine whether your material is more suitable to a global analysis approach or more suitable to a local singular field approach. And the method then fixes, if you like, calibrates how you should therefore partition the data. So on this note, I'm simply going to say that we have many other issues or aspects that we're interested in. Many are similar to those that are used in composites. These are areas that we're currently working in. And I now are going to stop sharing the screen, and I'm going to pass over to Tassos to take us to the second part of the presentation.
Thank you, Bamber. Can we see this right now?
Yes, it's okay. You can see it.
It's okay?
It's okay.
Okay, thank you. So thank you again, Bamber. Thank you, Andy, for the introduction. So I will start now discussing and talk about the fracture of structural adhesive joints, so more on the structural engineering. I will try to be less technical than Bamber, in the sense that I will not talk a lot about, I will not show a lot of equations, and I will not talk a lot about analysis of results. I would also like to invite you to turn on your microphones if you want to participate and discuss a bit on this lecture. So we'll talk about adhesively bonded joints in structural engineering. And the first question that I would like to pose is what kind of joints do you have in mind? Bamber talked more about joints in automotive and aerospace, which we all know that a lot of joints exist there. But can you give me examples of other structures that also have a lot of adhesively bonded connections? I will start by giving a hint. Do you think that we have adhesive joints in bridges? Of course we do. We also have adhesive joints in buildings, although we don't have in mind a lot of composite buildings, but I will show some examples today for this. And of course, we have adhesive joints in wind turbine rotor blades, where we have huge amounts of material, of adhesives, that is used for the new wind turbine rotor blades that reach today, they reach even more than 100 meters in length. So if we go to the first application that I announced, bridges, we can see a lot of different types of composite bridges that have been introduced in the last, I would say, 20 years. And here I started with the most typical, or the first, if you like, type of composite bridges that we could see. These bridges are based on the peltruded elements, what we can see in this left side of the slide here. And these elements have been made in pieces and then glued together. So this green area here is adhesive. And probably not all of you are familiar with peltruded elements, but these are very simple materials, normally glass with polyester or even other types of resins. And they are made in a very, very simple way by having the rovings here that go into a resin of matrix, and then into a preformer, and then in a continuous fabrication method, we can have thousands of meters of this material very easily. And by using these materials now, we can do bridges like this one. Here is the Pontresina Bridge, has been installed in 1999 here in the east part of Switzerland. It's used for the winter sports. And the asset of this bridge is that it's very lightweight. You see, it is made of these peltruded elements. It is very lightweight, and during summer, the bridge can be easily removed from the river because the river brings a lot of water down, and it can destroy the bridge. So they just take the bridge and they put it on the shore of the river very easily. But of course, this is I would say, the ancient history of bridges. Lately, bridges of composite sandwich panels have been made. For example, I can show you this one, the Avanson Bridge, again in Switzerland. This is a 12 meters. This is a vehicular bridge for traffic, two lanes bridge for loads of up to 40 tons. The weight of the bridge, as you see here, it is only 9 tons. In comparison with a typical concrete bridge of this size, could be around 40 to 50 tons. So it's 1/4 of the weight. And as we can see here, the bridge has been made in 3 pieces, and then these 3 pieces were glued together. So here we see a typical joint, which is a typical adhesive joint, by using the very commonly used adhesive in structural engineering. In this type is a Cicadur 330 epoxy, two-component epoxy. So these joints can be, you see, okay, I'll come back to this later. So these joints can transfer the loads efficiently. Tests that we did here in our lab showed that the joint, of course, failed because this is the connection point, but it managed to transfer all the loads that were supposed to be transferred by this. What I wanted to talk here, I said I will come back later, is to come back also to the discussion of Bamber about the bond thickness and the quality of the joint. Although in aerospace, even in automotive, sometimes there is a big quality control behind joining. In structural engineering, this doesn't happen. And you see here, this is a typical photo that shows the hand application of the adhesive on the joint. So this is the steel girder, and on top here, the bridge would be posed and glued on the steel girder. And the joint was made by applying this adhesive by hand and just trying to align it as better as possible. So we see also adhesive joints in buildings, and although we don't have it in mind, a lot of composite buildings exist today. This is a typical, probably not a typical, but it's one of the first composite buildings in the world, I would say. It is still existing there. It has been built in 2000 in Basel, in Switzerland. This is a 5-story building and 50 meters high, and it is all composite. And the idea here was not the best use of composite, of course, but it was to replace the steel girders that we used here normally by composites. And these composite girders were made by gluing together, so adhesively bonded together, different elements, protruded elements. And we see again, this is a result of the 3-point bending test of this element. And here it is, by the way, here is a typical example of good joining technique. If for those of you that read the papers from Hartsmith, his first argument was that the joint should be the point where the failure does not happen in a connection. And here we see that the failure didn't happen in the bond line, but happened in the flange of this. Suppose we can call it an I-beam, an artificial I-beam. We have also other cases where we have composites in building applications. This is the roof of the Novartis entrance hall in Basel again. It has been built in 2006. And the concept is that we have a glass facade here. And on top of this, without any connection, we just pose a sandwich panel, which is 22 by 22 meters. And this sandwich panel has been made in pieces. And these pieces were glued again. Here you see the connection, were glued by using again the same epoxy resin on site. So again, a glued connection in buildings. And of course, this is not a UFO. This is the roof of the Apple campus in California. And this is made by using carbon composites, of course, glued again together. And of course, you recognize this. This is not a MacBook, but this is again the roof of the building. If I'm not wrong, this is the building of Apple in Chicago. So a lot of applications in buildings, a lot of applications in bridges, a lot of applications, again, of adhesively bonded joints in wind turbine rotor blades. Here I have a couple of examples. You can also see the references where I took these photos here, and for those that need to find more details. We see a lot of bonding in wind turbine rotor blades. Imagine that this blade can be 60 to 100 meters long, and all around, between the spar beam and the skins, you have adhesives. We have also adhesives on the leading edge. We have adhesives on the trailing edge. And the concept here, the difference, the big difference compared to the joints that we have already seen, is the thickness of the joint. Here, the bond line thickness, in certain cases, can be even 20 to 30, even 40 millimeters thick. And this is for a lot of reasons. One is to tolerate to tolerate the problems in manufacturing, like what we see here, a lot of voids in the material, and a lot of adhesive used in these cases. So I just brought here a schematic or a diagram showing the weight of a blade, typical blades of today. So if you see blades, for example, of 80 meters, their weight is around 10 tons. And you can imagine that in this case, we have 10 to 15% weight of adhesives. So we have, like, for a 60 meters blade, we have half a ton of adhesive used. So you can imagine how massive adhesive joints we can have in these cases. And of course, you can understand that these joints are not the typical fracture mechanic joints that we have seen before. They are structural joints and all have a different behavior. So what we can easily understand is that the requirements for these joints are different. We have to think about the adherence used. And here I saw a typical, this is a microscopic view of a typical pultruded element. This is the view where we see the fibers coming out. And this is the view from the side where the fibers are going in this direction. And we see the fibers in the unidirectional layer. And here we see fibers of matte layers at the end of the laminate. And what is interesting to see here is that in these cases, and depending on the loading that we have on the structure, we can have cracks moving in different paths in the material. And what we should keep in mind here is that if we move in different paths, then we can calculate different energy. It is easier, for example, to move the crack between the unidirectional fibers, and it is more difficult to move the crack in between the woven rollings, because there we have the connection of the fibers to each other, and there are crack stoppers, actually. So in these cases also, we should think about geometry, about the adhesives used, the quality control, which is almost non-existing, and the conditions, because all the joining here, remember this bridge that was made, the gluing was made on site, so the conditions are not controlled in this case. So the curing conditions, which are very important for each adhesively bonded connections, are not controlled at all in this case. Of course, the good news is that we can use the same testing methods for this type of joints. Although we have asymmetric joints due to thick adhesive bond lines or due to dissimilar adherence, the behavior of these joints is similar to the behavior of the typical fracture mechanics joints. So in this case, we can easily, we have to adapt, but we can use the mode 1, mode 2, and mixed mode loading fixtures, as we've seen earlier today, for testing this type of specimens. Of course, the fixtures in this case should be scaled up, because normally the specimens that we have when we test structural joints are much bigger than the typical specimens described in the standards. So as we see here, we have the mode 1, the mode 2, and the mixed mode testing. Of course, here I was expecting some correction. It's mode 1 and mode 2 and mixed mode testing. And in this case, we can either follow the typical methods for measuring the crack, or we can also use other methods. One that we used here was by having a video extensometer and putting these dots, as you can see here in the specimen, and then by measuring the relative distance between the dots of the specimen along the, so the crack comes from this side, and when this distance starts increasing significantly, we can set a measure where we have to do a preliminary testing program to set this this limit. When the relative distance increases more than a certain limit, then we can assume that the crack is at this point and it propagates. So by doing this testing, we can have the typical load displacement curves. Mode 1, I mean, I will not go into details to these graphs because you've seen them at least twice today. So this is the load displacement curve for mode 1, mode 2 mixed mode, and the dashed line here is the crack length propagation. And by using the typical methods like the ECM, the experimental compliance method, we can also calculate the G1, G2, and mixed mode, G total as we call it, as a function of the crack length. So these are the R curves. And of course, you already discussed about this, that we have first part, which is the development of the crack, of the crack bridging length. And then after this, we have the almost stable crack propagation, the same for mode 2, the same for mixed mode. The question is, in mixed mode, how can we do the partitioning of modes? Because here, we know that we have a G total. We can use the experimental compliant method, but we don't know how much G1 and G2 we have here in this case. And I will talk about this on the next slide. Before, I would like to discuss about the fiber bridging. As we've seen that it increases a lot. You remember this increase of the R curve. So in this case, we have fiber bridging because of fibers breaking and bridging the crack. The difference compared to the joints that you have seen earlier today, is exactly the thickness of the adhesive layer here, so the bond line thickness. And this makes the joint already, even if the crack propagates in a in a path very close to the adhesive, the joint by itself is asymmetric. So in this case, we have the typical fiber bridging, and in this case, what we see, and this is what we observed in some cases, we had the fiber, as we call it, a fiber roving bridging, which means a bundle of fibers. We can see it clearly here. A bundle of fibers were bridged together, and this, as we will see later on, increases significantly the resistance of the material to fracture. So what we could expect is that this fiber roving bridging would increase significantly the R curve of the material. So if we see, for example, in this case, the G over crack length, you remember the paths of crack propagation in different layers of the laminate. We have the crack initiation and we have the crack propagation level. And if we have a normal, like what we have here, a typical fiber bridging, we can expect to have this, for example, behavior for a path 2 crack. But in the case like what we can see here, where we have roving bridging, what happens is that after the first initial bridging length development that we have here, instead of continuing with the steady state crack development, we have a second increase, and this is because of this roving bridging. And in this case also, the crack shifted from path 2 to path 3, so it went deeper to the material. What we can also do in these cases where we have a lot of bridging, we can use finite element with cohesive zone modeling and also finite element method with VCCT, the virtual crack closure technique. And by using this combination of finite element techniques, we can decompose the G total to G bridging and G tip. So G tip is the energy needed to open the crack tip, and bridging is the energy needed to propagate the crack when bridging appears. And then if we have the total energy, we can, for mode 1 or mode 2, we can decompose this and we can give directly the energy for bridging and the energy for tip. You can see that the G tip is always a stable value, and G bridging depends on the length, where we have either less or more bridged fibers. And what about G in mixed mode? As we said before, we can do the calculation for the G total, but then we cannot decompose. And to decompose the G in mode 1 and mode 2, there are quite a lot of methods. Initially, a method, it was called the global method, developed by Gordon Williams a long time ago. And it was based on the experimental compliance method. And actually, it was based on the decomposition of mode 1 and mode 2, depending on the thickness of the different arms of the laminate that was bended. But as we said here, we don't have only, in this case, when we have protruded material, for example, we don't have only differences in thickness, but each one of the arms of the joint have also different stiffness. So we, let's say, develop this method by using the ratio of the stiffness of the two arms. And by using this, and with some simple equations, you can find all the details in this reference. By using this, we can decompose the total energy based on mixed mode testing in mode 1 and mode 2. And here I would also show some examples where we, in this case, we had a mixed mode case where G1 and G2 were similar. And then we have, as you see here, we have only slightly higher G1 because the ratio is 1:0.8 and lower G2. And then if we have done this decomposition, then we can take these two components and we can continue by decomposing the G bridging and the G tip for each one of these cases. And then if we see, for example, case where G1 is much more than G2, we have different decomposition and so on. I will not go into details for this. Everything can be found as said in this in this paper, where it has been published back in 2014. So what is probably interesting here is that as we go higher in ratio of G2 on the G total, so more G2 in the G total, then we see that the G total is also increasing. And this reminds what Bamber said before, that normally, or usually I would say, for most of the materials, G2 is much higher compared to G1. And that's why here, when we have more G2 component, then the G total is higher. So what can we do if we have characterized the material under G1, G2, and mixed mode conditions? The first thing that we can do is to have a quasi-static fracture failure criterion. And this quasi-static fracture failure criterion can help to calculate intermediates, so do an interpolation, either linear or polynomial. It doesn't matter which kind of fitting equation we have here. But if we have this criterion, we can estimate intermediate values for mixed mode conditions. And of course, if we use these finite element methods that we described before, we can do the same, decomposing also the G bridging and G tip components. And how does this help now to analyze structural joints? If we assume, and I will just show very briefly this example here, if we assume that we have a structural joint with the same, made from the same material as the fracture mechanics joints, and having cracks propagating in similar path as those cracks propagating in the fracture mechanics joints, then we can analyze this by a finite element and calculate the mode mixity for each crack length in this joint. We have to point out, or we have to remember that as the crack propagates here, the mode mixity of this joint is changing. So if we know this mode mixity, and don't forget what we said about the same path, we can go back to the failure criterion that we developed before, and we can predict, if you like, the load displacement curve of this joint, and we can also predict the R curve for this joint. These are the progressive damage modeling that we developed in this sense, and also the experimental results. So we see that it is very, very important to define the material properties first. So we can assume that these are the material properties, the energy needed for G1, for G2, and the mixed mode. And then we can, in theory, we can use it to predict the behavior of any, in theory again, structural joint, taking into account that it follows the same fracture pattern as the joints, the fracture mechanics joint that have been analyzed. I don't want to bother you anymore with this. I think it's enough for now. I would like to thank you for your attention and give the word back to Andy for the continuation.